For more than 4.5 millennia, humanity has believed it understood the shape of the Great Pyramid. 4 sides, 4 corners, a singular mass of stone rising cleanly from the desert, immutable and complete. It appears in textbooks as a perfect geometric primitive, a monument so familiar that it feels solved, known, finished. But that certainty is an illusion. When the pyramid is lifted from the ground, not physically but perceptually, when it is viewed from the air or caught under a rare and precise angle of sunlight, the structure begins to fracture, not collapse but reveal. The smooth faces we thought we knew subtly divide. Lines emerge where no lines were meant to be seen. The pyramid does not remain 4-sided. It becomes something else entirely. Each face bends inward, ever so slightly, splitting into 2 planes, not warped by age, not eroded by wind, but shaped, deliberately. The Great Pyramid is not 4-sided at all. It is 8-sided, its geometry concealed so perfectly that it can pass unnoticed by millions standing at its base, and even by centuries of scholars who believed they had measured it completely. No ancient text describes this form, no inscription explains its purpose, and no practical necessity demands it. Yet it exists, and the deeper modern science looks, with aerial photography, satellite imaging, laser scanning, and mathematical reconstruction, the more resistant this geometry becomes to simple explanations. The indentations are too precise to be accidental, too consistent to be a structural failure, too symmetrical to be ignored. This is not a flaw, it is a choice. The Great Pyramid begins to feel less like a static monument and more like a problem, one that refuses to resolve itself, a structure that behaves differently depending on how it is observed. From the ground, it reassures. From above, it destabilizes, which raises a more unsettling question. Was this monument ever meant to be admired in the way we admire it now? Or was it designed for something else entirely, for alignment, for measurement, for interaction with forces larger than the human eye? To understand the pyramid's secret geometry, we must begin by letting go of the version we thought we knew. Because the greatest obstacle to understanding this structure has never been time or erosion or lost knowledge, it has been our assumption. For generations, the Great Pyramid of Giza has occupied a comfortable place in the human imagination. It appears orderly, stable, resolved. A 4-sided monument rising from the desert with mathematical calm, as if geometry itself had decided to fossilize into stone. It is taught this way in classrooms, rendered this way in diagrams, and remembered this way in popular culture. 4 faces, 4 corners, a perfect pyramid. That image has endured not because it is true, but because it is convenient. The human mind prefers clean shapes. We like monuments that feel finished, problems that appear solved. And for more than 4,000 years, the Great Pyramid has been treated not as a question, but as an answer. A relic from a distant past, impressive, yes, but ultimately static. Something to admire, not interrogate. Yet this certainty did not come from the ancient builders. It came from us. When early modern scholars first approached the pyramid with measuring tools in the 19th century, they were already carrying assumptions inherited from classical geometry. A pyramid, by definition, had flat faces. Any deviation from that ideal was assumed to be damage, erosion from wind, settling of stone, the long fatigue of time. The possibility that the deviation itself might be intentional barely entered the conversation. One of the most influential figures in this story was Sir William Flinders Petrie. In the 1880s, Petrie conducted the most precise survey of the Great Pyramid ever attempted up to that point. His measurements were meticulous, obsessive even. He catalogued angles, lengths, alignments, and deviations with a rigor that would define Egyptology for decades. And yet, even Petrie encountered something strange. Along the central lines of the pyramid's faces, his data hinted at subtle inward deviations, minute, almost imperceptible concavities. They were small enough to be dismissed, and so they were. Petrie attributed them to stone settling, construction irregularities, or later damage. After all, the deviations did not fit the model. And when data conflicts with belief, belief often wins. This was not negligence, it was limitation. 19th century metrology was constrained by the tools of its time. Measurements were taken from the ground with lines of sight interrupted by scale, perspective, and human error. There was no aerial vantage point, no satellite imagery, no laser scanning, no way to step back far enough to see the structure as a whole rather than as a collection of stones. From the ground, the pyramid reassures. Its faces appear flat, its symmetry appears absolute. The illusion holds. And so the idea of concavity, of faces that bend inward with deliberate subtlety, was folded into the category of imperfection, a footnote, not a revelation. This decision shaped the next century of interpretation. As Egyptology matured, the Great Pyramid became increasingly framed as a solved object. Its dimensions were catalogued, its chambers mapped. Its purpose, while debated in detail, was broadly agreed upon. The pyramid was a tomb, a monument to royal authority, a feat of logistics and labor. Extraordinary, but ultimately human. Ancient, but not alien. The shape itself was no longer questioned. Yet precision has a habit of hiding where expectation refuses to look. As the 20th century progressed, new technologies quietly began to erode old assumptions. Aerial photography, first from balloons then aircraft, offered perspectives no ancient surveyor or modern archaeologist had ever possessed. From above, under certain lighting conditions, faint lines appeared along the pyramid's faces, not cracks, not shadows cast by erosion, but symmetrical divisions running vertically down the center of each face. When these images were examined carefully, a troubling implication emerged. Each face of the Great Pyramid is not flat. It is composed of two planes, angled very slightly inward toward a central seam. Multiply this across all four sides, and the pyramid does not have four faces at all, it has 8. This was not damage. The concavity was too consistent, too symmetrical, too precise. It appeared on every face, aligned with the structure's cardinal orientation. The angles matched, the pattern repeated. The pyramid had been hiding its true geometry in plain sight. What had once been dismissed as error now demanded a different explanation. Because errors do not repeat with such discipline, erosion does not carve symmetry, settling does not respect cardinal directions. Intent does. The Great Pyramid began to look less like a relic frozen in time and more like an unresolved measurement problem. A structure whose most important features might not announce themselves loudly, but instead require patience, perspective, and humility to perceive. This reframing changes everything. If the pyramid's geometry includes features invisible from the ground, then it was not built solely for the human observer standing at its base. Its design anticipates viewpoints that feel almost anachronistic, angles of observation that suggest distance, elevation, abstraction. It invites measurement more than admiration. Seen this way, the pyramid stops behaving like a monument and starts behaving like an instrument, not one with moving parts or inscriptions explaining its function, but one whose meaning is encoded in proportion, alignment, and restraint. The assumption that broke, then, is not simply about the number of faces. It is the assumption that ancient builders worked only at the scale of immediate perception, that their designs were meant to be read instantly, understood intuitively, and consumed visually. The Great Pyramid resists that model. It withholds information, it conceals precision, it rewards distance rather than proximity. And that is deeply unsettling, because it forces us to reconsider the mindset of its creators. These were not builders content with approximate symmetry. They were not improvising with stone. They were executing geometry with a patience and subtlety that survives millennia and still escapes casual notice. Precision here is not loud, it is disciplined. As modern science continues to peel back layers of assumption, the Great Pyramid refuses to collapse into a single explanation. Instead, it sharpens into focus as something far more uncomfortable, a structure whose true complexity was underestimated not because it was primitive, but because it was too refined. And if this is only the beginning, if the very shape of the pyramid was misunderstood for centuries, then what else have we failed to see? If you're finding yourself questioning long-held certainties already, consider staying with this journey. Subscribing simply ensures you don't miss what comes next, as we continue to examine this structure not as legend, but as geometry that refuses to be dismissed. In 1926, aircraft of the Royal Air Force passed over the Giza Plateau during routine aerial reconnaissance. The photographs they captured were not intended to challenge archaeology. They were not searching for hidden truths. Yet within those black and white images, something quietly destabilizing appeared, something no one standing at the base of the pyramid could ever have seen. Under the oblique angle of the sun, each face of the Great Pyramid revealed a faint but unmistakable line running vertically down its center. Not a crack, not a shadow cast by damage, a division. At first, it was easy to dismiss. Photography was still a developing technology. Film distortion, lighting artifacts, and perspective anomalies were common explanations. But as decades passed and aerial imaging improved through satellites, high-altitude photography, and eventually digital photogrammetry, the lines did not disappear. They sharpened. What researchers slowly came to understand was unsettling in its simplicity. Each face of the pyramid is not a single flat plane. It is composed of two planes, angled inward by a fraction of a degree toward a central seam. This produces a subtle concavity, so slight that it escapes detection at ground level, yet so consistent that it repeats identically on all four sides. 4 faces become 8. This was not a matter of interpretation, it was geometry. Careful measurements confirmed that the concavity was deliberate. The angle of indentation measured across multiple surveys averaged just under 1 degree. Too precise to be accidental, too uniform to be structural failure, and crucially, too symmetrical to be the result of erosion or later damage. The pyramid had been split, not by time, but by design. To understand why this escaped notice for so long, one must consider the limits of human perception. From the ground, the Great Pyramid overwhelms the senses with scale. Its faces stretch upward at an incline shallow enough to deceive the eye into perceiving flatness. The brain, confronted with vast uniform surfaces, simplifies what it sees. It smooths irregularities. It assumes continuity. The concavity operates below the threshold of casual observation. At ground level, the deviation from flatness is measured in centimeters across tens of meters. It is not dramatic. It does not announce itself. Only when sunlight strikes the faces at a shallow angle, early morning or late afternoon, and only when viewed from above or at significant distance does the geometry reveal itself. This is not accidental concealment, it is optical restraint. Modern photogrammetry has made this impossible to ignore. By stitching together thousands of high-resolution images taken from multiple angles, researchers have reconstructed the pyramid's surfaces in 3 dimensions. The results are unequivocal. Each face is composed of 2 planar surfaces meeting at a subtle inward angle. The seam runs precisely along the centerline of each face, aligned with the pyramid's cardinal orientation. This alignment matters. If the concavity were random, the seams would wander. If it was structural collapse, the angles would vary, but they do not. They are disciplined, repeated, controlled, and they are unique. No other pyramid in Egypt, large or small, exhibits this feature with comparable precision. Not Khafra's pyramid nearby, not Menkaur's, not the older step pyramids, not the later attempts at smooth-sided construction. The Great Pyramid stands alone in this regard. This uniqueness raises an uncomfortable question. If concave faces were an architectural solution to a common problem, why were they not reused? If they were a structural necessity, why do other pyramids remain flat? The absence of this feature elsewhere suggests that it was neither experimental nor accidental. It was intentional and singular. One explanation proposes that the concavity improved structural stability by locking casing stones more securely. Another suggests it compensated for optical illusion, preventing the faces from appearing convex under harsh sunlight. These ideas have merit, but they fail to fully account for the precision involved. A rough adjustment would suffice for structural or visual correction. This was not rough. The angles are too exact, the symmetry too complete. The pyramid's eight-sided geometry seems less like a correction and more like a statement, one expressed not in writing or symbolism, but in form. A message encoded in stone that resists translation into simple function. What makes this even more remarkable is the discipline required to execute it. Each casing stone had to be placed not merely in alignment with its neighbors, but in service of an invisible curve spanning the entire face. The builders were not stacking blocks, they were sculpting planes. Planes that only resolve themselves when viewed from a vantage point no ancient observer could physically occupy. This implies a conceptual leap. The builders were not working solely from what they could see. They were working from what they could calculate. Geometry here is not decorative. It is anticipatory. The Great Pyramid begins to resemble a structure designed with abstraction in mind, one that assumes a viewer capable of stepping back, of seeing the whole rather than the part. In this sense, the pyramid is less concerned with immediate legibility than with long-term coherence. It rewards distance. It punishes haste. And so the moment of discovery, the day the pyramid split into 8 sides, was not a revelation of new construction, but a revelation of old blindness. The geometry had always been there, waiting for perspective to catch up. This reframes the pyramid entirely. It is no longer a static object frozen in antiquity. It is an active participant in perception, revealing different truths depending on how, when, and from where it is observed. If this geometry was intentional, and the evidence increasingly suggests that it was, then its concealment becomes as significant as its existence. At first glance, the concavity of the Great Pyramid's faces invites a simple explanation. Stone is heavy. Time is relentless. Gravity settles everything eventually. It is tempting, comforting even, to believe that the inward bend along each face is nothing more than structural fatigue slowly written into limestone. But that explanation collapses the moment it is tested. At the scale of the Great Pyramid, concavity is not required for stability. In fact, it is unnecessary to the point of being counterintuitive. A true, flat-faced pyramid distributes its weight efficiently downward and outward, channeling immense mass into a broad base. This is why pyramidal forms are among the most stable shapes ever conceived. They resist collapse precisely because their geometry is simple. If anything, introducing concavity complicates that simplicity. Structural engineers who have modeled the pyramid's load paths consistently arrive at the same conclusion. A flat-faced pyramid of Khufu's dimensions would have remained stable for millennia without any inward bending. The compressive strength of limestone, combined with the pyramid's enormous base-to-height ratio, already provides more safety margin than necessary. There is no structural advantage gained by indenting the faces inward by a fraction of a degree. This is not speculation. Modern finite element analyses, tools used to test skyscrapers and dams, demonstrate that the pyramid's stress distribution remains well within tolerances even when modeled with perfectly flat faces. The concavity does not meaningfully reduce stress. It does not prevent slippage. It does not reinforce corners. In short, it does nothing that engineering demands, which leaves only one conclusion. If the concavity exists, it exists by choice. The improbability deepens when one considers symmetry. Natural deformation does not repeat itself with mathematical discipline. Stone settles unevenly. Temperature fluctuates. Foundations shift. Over centuries, these processes introduce noise, randomness. Yet the Great Pyramid displays none of this chaos. Each face curves inward at nearly the same angle. Each central seam aligns precisely with the pyramid's cardinal orientation. Each deviation mirrors the others. Statistically, this matters. When engineers analyze construction error, they expect deviations to follow a distribution. Some faces slightly flatter, others more distorted. Some sides leaning outward, others inward. Errors accumulate independently, they do not coordinate, but the pyramid's concavity is coordinated. Error distribution analysis shows that the likelihood of 4 massive faces independently deforming inward by the same degree, along the same axis with the same symmetry, approaches 0. This is not random drift. It is not cumulative damage. It is not chance, and it is signal. To appreciate just how deliberate this must have been, one must look closely at the tolerances involved. The casing stones of the Great Pyramid, now mostly lost but documented through surviving examples and early accounts, were fitted with astonishing precision. Joints between stones were often thinner than 0.5 millimeter. In some cases, a blade cannot be inserted between them. This level of accuracy rivals, and in certain respects surpasses, medieval masonry. Gothic cathedrals, masterpieces of stone construction, display joint tolerances several times larger. Even many modern stone buildings, constructed with steel tools and laser-guided equipment, struggle to maintain such consistency across large surfaces. And yet, the pyramid achieved this precision without iron tools, without precision measuring devices as we understand them, and without written blueprints that survive to explain the process. Now consider what concavity demands. To produce a flat face, masons must align stones to a plane. To produce a concave face, they must align stones to a plane that subtly changes orientation across its width. Each stone must be placed not merely in relation to its neighbors, but in relation to an invisible curve that spans tens of meters. Deviate too much, and the curve collapses into flatness. Deviate too little, and the effect disappears entirely. This is not easier than flat construction. It is harder. It requires foresight, measurement, consistency across thousands of placements, and crucially, it requires a reference system capable of maintaining the same geometry on all 4 sides of a structure that rises nearly 150 meters into the air. Such precision is not accidental labor, it is intentional geometry. Some have suggested that the concavity might be an artifact of construction sequencing, that stones were placed inward to accommodate ramps or scaffolding, and the shape simply persisted. But this explanation fails under scrutiny. Temporary construction features leave irregular traces. They do not produce clean, symmetrical planes that resolve into a coherent geometric pattern when viewed as a whole. Others argue that the concavity might be a visual correction, compensating for optical illusion, preventing the faces from appearing convex under bright sunlight. Yet even this explanation raises questions. Optical corrections typically exaggerate features so they are noticeable. The pyramid's concavity does the opposite. It hides itself. It is too subtle to serve as a correction for the human eye at ground level, which suggests that the intended observer may not have been standing at the base at all. When geometry exceeds structural need, it often signals a different purpose. In architecture, unnecessary precision is rarely wasted. It usually communicates something: status, knowledge, control, or worldview. The Great Pyramid's concavity communicates restraint. It suggests an intelligence comfortable with embedding complexity without explanation. This is where modern comparisons become instructive. When contemporary architects pursue precision beyond necessity, it is often for symbolic or informational reasons. A building may encode proportions tied to mathematical constants. A monument may align with celestial events. A structure may incorporate geometry that speaks to cosmology, power, or permanence. In these cases, the building becomes a language. The Great Pyramid appears to participate in this tradition, except it predates it by thousands of years. The refusal of its geometry to align with structural necessity forces a reconsideration of the builder's intent. These were not laborers improvising solutions to engineering problems. They were executing a design whose priorities extended beyond survival and utility. They were embedding order into stone, confident that it would persist, even if its meaning did not. This confidence is striking. It implies that the geometry was not meant to be explained verbally or even immediately understood. It was meant to endure, to remain measurable long after the culture that built it had vanished. In this sense, the pyramid is less like a message carved into stone and more like a proposition set into space. A question posed in geometry. The concavity, then, is not a flaw. It is a clue, a sign that the pyramid's shape cannot be reduced to accident, erosion, or convenience. It belongs to a category of design where precision is not justified by function alone. And that leaves us facing a deeper problem. If the geometry was not structural, if it was not correcting, reinforcing, or stabilizing, then what was it doing? What kind of language speaks through angles so subtle they evade casual sight, through symmetry so strict it defies randomness, through precision that exceeds necessity? The Great Pyramid does not answer that question. It simply insists that it be asked. The concave geometry of the Great Pyramid would likely have remained a marginal curiosity if it were not for one decisive factor: light. Not symbolism, not mythology. Sunlight, behaving according to strict physical laws, became the mechanism that made the geometry legible. This is not a poetic coincidence. It is optics. A flat surface reflects light uniformly. A concave surface does not. Even a shallow inward angle, when extended across a surface as large as the Great Pyramid's faces, alters the way light and shadow behave in measurable ways. This is why the pyramid's eight-sided form does not reveal itself consistently. It appears only when the sun is positioned low in the sky, striking the faces at a shallow angle that exaggerates minute changes in surface orientation. At high noon, the sun is nearly overhead. Light strikes the pyramid's faces almost perpendicular to the surface. Under these conditions, differences between planar surfaces are minimized, shadows shorten, subtle geometry disappears into uniform brightness. To a ground observer, the pyramid looks flat, stable, and geometrically simple. But as the sun lowers, early morning or late afternoon, the physics changes. Light approaches the surface obliquely. Small deviations in angle produce longer, more sensitive shadow gradients. The inward bend at the center of each face begins to cast a faint but continuous line of shadow. The pyramid's face divides visually into two planes. This is not subjective, it is repeatable. Architectural optics research shows that concavities of less than 1 degree can remain invisible under direct illumination, but become detectable under grazing light. The threshold depends on 3 variables: surface roughness, angle of incidence, and observer distance. The Great Pyramid satisfies all 3 conditions required for delayed visibility. Its faces are vast, its stone surfaces are relatively smooth at scale, and the concavity is consistent across tens of meters. The geometry is therefore not hidden, it is conditional. This conditional visibility becomes even more interesting when examined across the solar year. Studies of illumination patterns at Giza show that the concavity lines are most clearly defined near the equinoxes, when the sun's path produces near-symmetrical lighting on the pyramid's east and west faces. During these periods, the sun rises and sets due east and due west, aligning closely with the pyramid's cardinal orientation. This alignment matters because the concavity seams themselves run precisely along the center line of each face, which is aligned to the cardinal directions. When light approaches from due east or west at low angles, it interacts symmetrically with the 2 planar halves of each face. One plane catches light slightly sooner, the other falls into shadow slightly earlier. The seam between them becomes visible not as a line carved into stone, but as a boundary defined by light behavior. The pyramid, in effect, uses the sun to outline its own geometry. This does not require symbolic interpretation. It requires only an understanding of how light behaves on angled surfaces. Modern architects exploit the same principles when designing facades that change appearance throughout the day. The difference is that such designs are meant to be noticed. The Great Pyramid is not. The solstices introduce a different but related phenomenon. At the summer and winter solstices, the sun reaches its extreme positions north and south. The angle of illumination changes accordingly, emphasizing different faces and suppressing others. Observations show that under these conditions, concavity visibility shifts subtly. The lines may appear stronger on one face and weaker on another, depending on solar azimuth. This variability reinforces an important point. The geometry is not decorative, it is responsive. The pyramid does not display its full shape constantly. It reveals it episodically in response to predictable astronomical conditions. This is what makes the structure behave less like a static monument and more like a passive instrument, one that does nothing actively, but responds precisely to external input. The term instrument here is not metaphorical. In scientific terms, an instrument is any system designed to respond in a consistent, measurable way to a physical stimulus. The Great Pyramid responds to light. Its geometry transforms illumination into information. This interpretation is supported by solar angle calculations. At Giza's latitude, the sun's altitude at sunrise and sunset during equinoxes produces grazing angles well within the sensitivity range required to reveal sub-degree concavities. The builders did not need advanced mathematics to know this. They needed observation, repetition, a long familiarity with the sun's path across the horizon. What they encoded was not an abstract calendar, but a physical interaction. Importantly, this interaction does not rely on human presence. The pyramid does not need observers. The light and shadow behavior occurs whether anyone is watching or not. This distinguishes it from structures explicitly designed for ritual viewing. The pyramid's geometry activates regardless of the audience. This has implications. If the concavity were meant to be seen regularly, it would be exaggerated. If it were meant to communicate symbolically, it would be accompanied by inscriptions or iconography. Instead, it operates silently, precisely, and rarely. It reveals itself only under conditions that require patience and long-term observation. Smithsonian-affiliated studies on ancient solar alignment emphasize that many early monumental structures use light as a diagnostic tool rather than a display. They mark transitions, validate orientation, or confirm alignment. The Great Pyramid's interaction with light fits this category more comfortably than it fits symbolic solar worship. The geometry does not celebrate the sun, it tests it. Architectural optics research further undermines accidental explanations. When concave planes are unintended, light behavior is irregular, shadow lines wobble, visibility varies unpredictably. In the Great Pyramid, the illumination patterns are stable across years and repeatable across observations. This implies control, not merely in construction, but in conceptual design. The pyramid's faces were shaped with an understanding that light would eventually interrogate them. This reframes the structure again. The pyramid is not simply aligned to the sun, as many ancient monuments are. It is calibrated against it. Its geometry is verified by solar motion, not explained by it. Crucially, none of this requires invoking hidden knowledge or lost sciences. The physics involved is basic: angle of incidence, reflection, shadow length. These are principles accessible to any culture that builds, observes, and measures over time. What is extraordinary is not the knowledge itself, but the restraint with which it was applied. The concavity is tuned so finely that it skirts the edge of visibility. It exists at the threshold where light can reveal it, but only just. This suggests intentional moderation, a geometry designed not to impress but to persist, which brings us to an unavoidable question. If ancient builders went to such lengths to encode geometry that only light at certain times from certain angles could reveal, geometry that serves no structural necessity and announces no symbolic message, then why design it that way at all? Why would a civilization invest precision into a form that requires the sun itself to decode it? Long before the geometry of the Great Pyramid reveals itself through light, another precision asserts itself silently, one that does not depend on illumination at all. It is embedded in the way the structure sits upon the earth. The Great Pyramid is aligned to true north with an accuracy that still unsettles modern surveyors. Measured deviation is commonly cited at around 3 to 4 arc minutes, approximately 0.05 degrees. To place that in context, this is an error of less than 1/12 of a single degree across a base that spans more than 230 meters. In linear terms, the northward deviation amounts to only a few centimeters from perfect cardinal alignment. This is not an exaggeration born of romanticism. It is a measured fact, repeatedly confirmed by independent surveys over more than a century. What makes this remarkable is not merely the number, but the era. Modern land surveyors equipped with theodolites, GPS, and laser-based total stations routinely achieve similar accuracy, but only with instruments designed specifically for that purpose. Even then, alignment to true north is not trivial. Magnetic north is unreliable. Grid north is artificial. True north must be calculated, corrected, and verified. The builders of the Great Pyramid had none of these tools. No compass, no global coordinate system, no written trigonometry as we understand it. Yet the pyramid's sides are aligned more accurately to true north than many medieval cathedrals, Renaissance palaces, and even some 19th century public buildings. This demands explanation, not admiration. Early Egyptologists initially assumed coincidence or gradual correction. Perhaps builders adjusted alignment as construction progressed. Perhaps minor errors cancelled out. But when all 4 sides were measured, the pattern refused to cooperate. The deviations were not random, they were consistent and systematic. The pyramid was not close enough to the north. It was deliberately placed there. The most compelling explanations abandon the ground entirely and look upward. One of the leading hypotheses, advanced by Egyptologist Kate Spence and published in the journal Nature, proposes that the builders used circumpolar stars, stars that never set but rotate endlessly around the north celestial pole. Around 2500 BCE, 2 such stars, Kochab in Ursa Minor and Mizar in Ursa Major, formed a near-vertical alignment when observed simultaneously. By citing the moment when these stars crossed a vertical line, ancient observers could establish true north with remarkable accuracy. This method requires no advanced mathematics. It requires patience, clear skies, and repeated observation. Crucially, it also requires an understanding of celestial regularity, the knowledge that the sky moves predictably night after night. Spence's hypothesis does more than explain the alignment. It explains its precision. Because Earth's axis slowly wobbles, a phenomenon known as axial precession, the position of the celestial pole shifts over time. This means that the stellar alignment used to find north would change subtly from century to century. When the orientation errors of the Great Pyramid and its neighboring pyramids are plotted against construction dates, a pattern emerges that matches precession-based prediction remarkably well. In other words, the small deviations are not noise and they are timestamps. This is a critical point. It suggests that the pyramid's orientation was not only deliberate but also astronomically informed and temporally specific. The builders were not approximating north. They were calculating it relative to a sky that they knew was changing, slowly but measurably. Egyptological surveying literature reinforces this conclusion. Studies comparing the orientation of Old Kingdom pyramids show systematic variation consistent with stellar alignment methods, not solar ones. Solar shadow methods, while simpler, cannot achieve the level of precision observed. They introduce errors far larger than those measured at Giza. Stellar methods, by contrast, can, but stellar alignment introduces a deeper implication. To use circumpolar stars effectively, observers must conceptualize north not as a direction on the ground, but as an axis extending into the sky. They must think three-dimensionally, mapping terrestrial orientation onto celestial motion. This is not a casual observation, it is applied cosmology. The Great Pyramid, then, is not merely aligned with the Earth. It is aligned with Earth's relationship to the cosmos at a specific moment in time. Modern surveying comparisons sharpen the discomfort. When professional surveyors are asked to establish true north without electronic aids, using only sighting, timekeeping, and celestial observation, their average error often exceeds that of the pyramid. Not because they lack skill, but because the task is genuinely difficult. Accuracy improves with repetition, with tradition, with a culture that values alignment as more than convenience. Which raises an important question. Why was this alignment so important? From a structural perspective, perfect cardinal orientation offers no meaningful advantage. A pyramid does not become stronger by facing north. It does not become easier to build. It does not resist earthquakes more effectively. Orientation is irrelevant to stability. From a functional perspective, orientation matters only if something external is being referenced: the sun, the stars, the Earth itself. The Great Pyramid's orientation suggests that its builders cared deeply about absolute reference frames. They were not content with local landmarks or approximate directions. They anchored the structure to a global axis, one defined by planetary rotation. This shifts our understanding of the monument again. It is no longer simply a building placed on land. It is a structure inserted into a coordinate system. The combination of near-perfect north alignment and precisely controlled face geometry begins to look less like coincidence and more like integration. Orientation and shape are not independent features. They are part of a single design logic, one that treats the pyramid as a fixed point within a larger spatial order. The builders could have oriented the pyramid approximately north. They could have aligned it visually with nearby structures. They could have accepted a degree or two of error. Many ancient cultures did exactly that. They did not. Instead, they achieved a precision that demands explanation, achieved through methods that require long-term astronomical observation, disciplined measurement, and a conceptual framework that links sky and stone. And yet, even this achievement leaves something unresolved. We can explain how the pyramid was oriented, we can model the stars, we can account for precession, we can reconstruct the methods. What remains elusive is why this precision was necessary, why orientation mattered so deeply that it justified such effort, such care, such restraint. The pyramid sits exactly where it is meant to sit, but that does not yet tell us why it is shaped the way it is. The orientation problem can be accounted for by the sky. The geometry problem cannot. Once the Great Pyramid is fixed to true north, another layer of discipline becomes visible, one that operates entirely within the structure itself, not symbolism, not alignment, but internal mathematical coherence. Across all four faces, the slope angle is effectively identical. Modern measurements place the angle of inclination at approximately 51 degrees 50 minutes 40 seconds, with variations so small that they fall within construction tolerance rather than design inconsistency. Each face rises at the same angle, meets at the same apex geometry, and preserves proportional relationships from base to summit. This uniformity is not a given. Ancient large-scale stone structures frequently show angular drift, slight changes in slope caused by cumulative error, material variation, or adaptive correction during construction. Even skilled builders struggle to maintain identical angles across independent planes without a governing mathematical framework. Here the framework is visible. The Egyptians did not describe slope using degrees. They used a system known as the seked. The seked defines slope as the horizontal displacement corresponding to a vertical rise of 1 cubit. In simpler terms, instead of saying this wall rises at 52 degrees, an Egyptian builder would say, for every cubit up, it moves this many palms outward. This system is documented explicitly in the Rhind mathematical papyrus, circa 1650 BCE, which preserves much older mathematical traditions. Several problems in the papyrus deal directly with pyramid slopes, asking the reader to calculate the seked given a height and base, or to determine dimensions from a known seked. The seked of the Great Pyramid corresponds to 5.5 palms per cubit. This is not an approximation. It is an exact rational value within the Egyptian measurement system. Using the royal cubit, approximately 52.36 centimeters, divided into 7 palms, a seked of 5.5 palms produces a slope that converts precisely to the measured angle of the pyramid. This means the builders were not aiming for an angle. They were executing a ratio. The slope exists because the ratio exists. This distinction matters. It shifts the pyramid from a product of visual judgment to a product of arithmetic intention. The builders were not checking angles with plumb lines alone. They were enforcing proportional rules across scale. When modern geometric reconstructions reverse engineer the pyramid using seked mathematics, the numbers close cleanly. Height, half base, and slope resolve into consistent relationships without residual error. No compensatory adjustments are required. This consistency extends beyond the faces. The ratio between the pyramid's half base and height closely approximates 14:11, a ratio that emerges naturally from the seked value. This ratio recurs in multiple internal dimensions as well, suggesting that the slope was not an isolated parameter but a controlling one. Once the slope is set, everything else follows. Change the slope slightly and the height shifts. Change the base, and the angle must adjust. But in the Great Pyramid, these variables lock together as if governed by a single equation. The Rind Papyrus does not describe the Great Pyramid directly, but it demonstrates that Old Kingdom mathematics was fully capable of such design. Problems show comfort with fractional arithmetic, proportional scaling, and geometric reasoning applied to monumental architecture. What the papyrus proves is not brilliance, but normalcy. This was not extraordinary mathematics for them. It was standard. Modern surveys reinforce this conclusion. Laser scanning of the pyramid's faces shows that angular deviation across each face is minimal, not only between faces, but within them. The slope does not wander, it does not flatten near the top or steepen at the base. It holds. This implies disciplined control over vertical rise and horizontal offset at every course. Each layer of stone had to satisfy the same seked relationship as the one below it. Errors could not be corrected later without breaking the slope. Which raises an uncomfortable implication. The geometry had to be decided before construction began. There was no room for improvisation. The apex could not be found gradually. It had to be inevitable, encoded from the first course upward. This requires a complete geometric conception of the finished structure before laying the foundation, not a sketch, a mathematical model. The consistency of slope also rules out several alternative explanations. The idea that the pyramid evolved during construction, changing plans mid-build, does not survive geometric scrutiny. Any such change would introduce measurable angular discontinuities. None are present. Likewise, theories suggesting symbolic angles chosen for religious reasons struggle unless they also account for arithmetic execution. Symbolism alone does not enforce precision across 4 independent planes over millions of stone blocks. Mathematics does. Some researchers have noted that the pyramid's slope produces ratios that approximate well-known constants when expressed in modern terms. While caution is necessary to avoid anachronism, it is undeniable that the geometry generates repeatable numerical relationships across different scales of the structure. The critical point is not whether the Egyptians knew modern constants, but that their system naturally generated stable ratios that propagate through the design. This is a hallmark of internally coherent geometry. The pyramid is not a collection of dimensions. It is a single proportional system expressed in stone. The seked is the key to understanding this. It converts three-dimensional form into a repeatable construction rule that can be applied by teams without abstract angle measurement. Workers do not need to have degrees. They need to know how far to step outward for each rise. This makes the precision even more striking, not less. Because it means thousands of individual actions, each stone placement had to conform to the same invisible rule. No single block defines the slope. The slope emerges from the collective obedience to proportion. That obedience suggests training, standardization, and oversight rooted in mathematical authority rather than ad hoc decision-making. Modern reconstructions, using only seked rules, reproduce the pyramid's geometry with startling fidelity. When height is fixed at approximately 280 cubits and the seked is set to 5.5 palms, the base resolves to the measured value within negligible error margins. The math closes. And it closes repeatedly. This is the defining feature of intentional geometry: repeatability. The numbers do not just work once, they work everywhere, which brings us to the unresolved tension. If the exterior geometry is governed so tightly, if slope, base, and height are locked into a single proportional logic, then the pyramid is not merely shaped, it is structured. And if structure governs the exterior so completely, it becomes increasingly difficult to believe that the interior is arbitrary. The same culture that enforced angular consistency across 4 monumental faces did not suddenly abandon mathematics once the casing stones were laid. If the exterior speaks in ratios and rules, then the interior is not a void. It is waiting, and whatever it contains will not contradict the geometry that encloses it. Within the limestone walls, hidden corridors and shafts complicate the narrative, suggesting that geometry was not limited to the visible planes. These internal passages challenge conventional assumptions about function and purpose. 2 sets of shafts extend from the pyramid's central chambers, those of the king's chamber and those of the queen's chamber. Unlike the straightforward passageways leading to the descending and ascending corridors, these shafts appear enigmatic in design. They are narrow, highly inclined, and terminate abruptly in solid stone or unreachable voids. Their dimensions are consistent, roughly 20 to 25 centimeters in width and height, running at angles between 39 and 45 degrees depending on the chamber. Yet, they do not form symmetrical pairs in the traditional sense. The Queen's chamber shafts incline slightly differently from the King's, and neither pair reaches the exterior in a way that suggests a clear functional exit. Early interpretations suggested ventilation. After all, a tomb containing a sealed sarcophagus might require airflow. Yet structural and environmental analysis makes this explanation implausible. The pyramid is massive, insulated, and designed to maintain stable internal temperatures. The chambers themselves do not contain materials or arrangements that would require continuous ventilation. Archaeological surveys show no trace of decay that would necessitate airflow for preservation. Even more revealing is the positioning of the shafts. In the king's chamber, the southern shaft rises at 45 degrees, terminating well below the pyramid's casing stones. The northern shaft at 32 degrees similarly does not penetrate the outer shell. Their lengths are precisely measured, each segment perfectly straight within millimeter tolerances. Yet, no functional necessity demands such precision for air circulation. A simple opening at the ceiling would suffice to provide ventilation or temperature equilibration. Rudolf Gantenbrink's pioneering robotic surveys in the 1990s confirmed this. Using remotely controlled vehicles, his team traversed the Queen's chamber shafts, documenting their straightness, consistent cross-section, and precise inclination. Each segment maintained an angle that would have required careful surveying during construction. Minor deviations exist, but only to accommodate minor limestone irregularities. The paths themselves display discipline, not improvisation. Architectural necessity analysis reinforces this anomaly. Engineers examining the shafts conclude that they do not contribute to the structural integrity of the chambers. Unlike relieving chambers above the king's chamber, which redistribute stress to prevent collapse, the shafts provide no load relief. They do not stabilize the roof, distribute weight, or serve as emergency egress. The walls around them are overbuilt for stability regardless of the shaft's presence. In purely functional terms, the pyramid would be structurally equivalent without them. Some researchers have proposed symbolic or religious purposes, suggesting the shafts point towards stars like Orion or Sirius. While intriguing, these hypotheses require caution. The angles are approximate, and the shafts do not exit the pyramid cleanly, making precise stellar alignment impossible without assuming advanced observational tools that leave no archaeological trace. Moreover, asymmetry between paired shafts undermines a strict star mapping function. The northern and southern shafts of each chamber do not mirror each other in a way that guarantees predictable celestial targeting. What the shafts demonstrate unequivocally, however, is meticulous angular design applied without apparent utilitarian justification. Measurements are telling. The King's Chamber northern shaft is inclined at 32.5 degrees, while the southern shaft rises at 45 degrees. The Queen's Chamber shafts show similar angular deviations. The northern shaft at roughly 39 degrees, the southern shaft at 40 degrees. These inclinations are not random. They are precise enough that, given the building techniques of the Old Kingdom, each stone placement along the shaft required deliberate calculation. A 1 to 2 degree deviation over such lengths would have been noticeable, yet the builders maintained tolerances within fractions of a degree. This precision is consistent with the broader geometric discipline observed on the exterior faces and slope ratios. The shaft's interior surfaces are equally precise. Limestone walls are dressed smooth, angles consistent across their lengths, joints carefully aligned. At junctions where the shaft changes direction slightly to avoid limestone blocks or structural features, the adjustment is gradual and calculated, not accidental. The craftsmanship suggests intention, but intention for what remains unclear. Attempts to rationalize the shafts as conduits for tools or ceremonial objects also fail under scrutiny. They are too narrow for practical transport of anything substantial. They are sealed at endpoints in ways that preclude repeated access. Archaeological inspection of the sealed ends shows no wear patterns consistent with routine use. In short, they do not appear to be functional corridors for people, objects, or airflow. The pattern that emerges is one of intentional, precise, and internally consistent angles without functional necessity. The builders applied the same level of discipline seen on the pyramid's faces and slope. Measurements, inclination, and placement were deliberate. The geometry persists even where it cannot be observed from outside the pyramid. The shafts are, in effect, invisible extensions of the pyramid's broader mathematical system. Gantenbrink's robotic explorations also revealed small limestone doors or blocks at the ends of the Queen's Chamber shafts, sometimes with copper fittings embedded. These features are puzzling. They appear intentionally placed with no clear functional explanation. They cannot be opened from outside, do not allow passage for air, and offer no structural advantage. Their existence reinforces the conclusion that the shafts were conceived as components of design, not as practical installations. Comparing the shafts to the rest of the pyramid reveals a conceptual continuity. The exterior concavity, orientation to true north, and slope ratios all emphasize measurement, repeatable geometry, and disciplined execution. The shafts extend this logic into the interior, demonstrating that the pyramid's internal layout is subject to the same mathematical principles, even where conventional function is absent. This observation raises deeper questions about intent. If the shafts do not provide ventilation, structural relief, or access, then their purpose must lie in another realm, one in which geometry itself conveys meaning. Their inclination, straightness, and asymmetry suggest a language embedded in angles rather than words. They are part of the same system that gave the pyramid its precise faces, consistent slopes, and cardinal orientation. Only here that language is internal, hidden from casual observation, yet executed with the same discipline. The shaft's very existence demonstrates a key principle. The pyramid is not merely a tomb. Nor is it merely a structure designed for human perception at ground level. Its interior angles, like its exterior faces, encode relationships that require measurement, calculation, and abstract thought. The builders were not improvising passages, they were following design rules that extend beyond necessity. If the king's and queen's chamber shafts were not intended for airflow, and if they were not structural, then they exist as geometry for its own sake. This is a radical notion in ancient architecture. Most monumental structures prioritize function or visibility. Here, precision is applied without the imperative of practicality. In that sense, the shafts are more telling than any decorative feature. They reveal the mindset of the builders, one committed to embedding patterns, angles, and rules into stone, even when those patterns cannot be experienced fully. Whatever the purpose, the shafts refuse to be accidental. Their placement, inclination, and execution demonstrate deliberate planning and consistency with the pyramid's broader proportional and geometric system. They hint at a logic that is partially visible, partially hidden, and fully intentional. The shafts of the Great Pyramid, with their precise inclinations and abrupt terminations, naturally invite speculation. For decades, researchers have suggested that they might encode astronomical knowledge, that the pyramid, in its silent complexity, aligns with stars whose positions were important to ancient Egyptians. Chief among these theories are the Orion and Sirius hypotheses, which propose that the king's chamber shafts point toward specific stars in the night sky around the time of construction. The Orion hypothesis, popularized in the 1990s by Robert Bauval, posits that the southern shaft of the king's chamber was aligned with Alnitak, the easternmost star in Orion's belt, while the northern shaft aligned with Thuban, which, due to precession, marked the North Pole around 2500 BCE. The Queen's chamber shafts, in this theory, are linked to Sirius and a secondary star in Orion's constellation. On the surface, the idea is seductive. The pyramid as a terrestrial mirror of the heavens, a precise astronomical instrument frozen in stone. Yet the hypothesis immediately encounters complications. First, the angles of the shafts do not match stellar altitudes with absolute accuracy. The southern king's chamber shaft is inclined at roughly 45 degrees, but Alnitak's rising angle relative to the horizon in 2500 BCE differs slightly, and the northern shaft at 32.5 degrees does not perfectly intersect Thuban's position. Minor errors may seem inconsequential, but the ancient builders were capable of precision within fractions of a degree, as seen in the faces and orientation of the pyramid itself. Why would they introduce inaccuracies in such a prominent feature? Second, precession complicates the picture. Earth's axis wobbles over a 26,000-year cycle, slowly shifting the positions of circumpolar stars. A shaft fixed rigidly into stone will inevitably drift out of alignment with a moving star over centuries. Any claim that the pyramid was precisely aligned to a particular star requires careful dating and astronomical modeling. Even slight miscalculations in construction chronology produce discrepancies of several degrees. Third, the shafts do not consistently reach the exterior, which raises a problem for observational utility. If these were intended to allow stargazing or light to enter the chambers along stellar lines, then their termination points would need to intersect the sky directly. Instead, both the Queen's chamber shafts stop within solid stone. The King's chamber northern shaft comes close, but still leaves ambiguity. In practical terms, this precludes using the shafts as telescopic sightlines or straightforward alignment devices. Modern astronomical modeling supports these limitations. Simulations of the night sky in 2500 BCE show that while the shafts roughly point toward Orion and Sirius, the alignment is approximate, and small differences, imperceptible to casual observation, become significant when trying to claim intentional celestial targeting. Furthermore, a symmetry between paired shafts, especially in the Queen's chamber, suggests that even if star alignment were considered, it was not applied consistently across the system. Bauval's hypothesis has inspired both fascination and critique. Scholars like Ed Krupp and researchers in the field of archaeoastronomy emphasize caution, arguing that correlation does not imply causation. Just because a shaft can be loosely matched to a star does not mean it was intended to do so. There is no written evidence or surviving manual explaining stellar alignment as a design requirement. The mathematical and geometric discipline visible elsewhere in the pyramid does not rely on observation of stars. It is also worth noting that stars themselves are dynamic reference points. Their altitudes and azimuths vary not only over millennia, but also due to nutation and proper motion. Achieving precise long-term alignment would have required tracking and projecting these movements centuries in advance, a task for which no historical documentation exists, though the Egyptians were skilled astronomers. Critiques further highlight that the shaft's primary design features, narrow width, sharp angles, and abrupt endpoints, do not reflect what is required for consistent celestial observation. The shafts appear optimized for their own internal geometry, rather than for accommodating sightlines or light paths. This reinforces the idea that if astronomical correlation exists, it may be incidental or symbolic, rather than functional. Despite these limitations, the star hypothesis remains tantalizing. Its appeal is partly aesthetic. The notion of the Great Pyramid as a reflection of the cosmos resonates with our desire to find cosmic order in human endeavor. Its appeal is partly empirical. The general proximity of Orion and Sirius to the shaft's directions cannot be dismissed entirely. There is, at the very least, a suggestive correlation, a hint that the builders were aware of celestial phenomena and may have referenced them in design choices. Yet here is the crucial distinction: suggestive is not conclusive. The pyramid's geometry, its concave faces, precise slope angles, and meticulous cardinal orientation exists independently of the stars. The engineering and proportional logic embedded in stone function as a measurable system, verifiable without invoking extraterrestrial reference points. Stars might overlay meaning onto this system, but they are not necessary to validate the geometry itself. Archaeoastronomical literature emphasizes this carefully. Papers in journals such as Archaeoastronomy and Ancient Science, and studies by scholars like Kate Spence, stress that while ancient Egyptian structures often demonstrate solar and stellar awareness, direct causal links are difficult to establish without corroborating documentation. The Great Pyramid exemplifies this tension. Precise architecture is undeniable, but interpretation remains open-ended. In practical terms, this means that even if Orion and Sirius were on the minds of the builders, the geometry stands independently. The concavity, slope, and orientation exist whether stars are referenced or not. The pyramid does not rely on a celestial explanation to justify its precision. The angles, ratios, and alignments are embedded in the structure itself. Thus, the star hypothesis must be approached with care. It can enrich our understanding, offering context or potential symbolic layers, but it cannot substitute for rigorous analysis of geometry and construction. Scholars, surveyors, and engineers alike emphasize skepticism, recognizing the suggestive nature of correlations while avoiding overstatement. Ultimately, the shafts and potential stellar connections illustrate a key point. The Great Pyramid is multidimensional in its precision. Its exterior, slope, orientation, and interior passages all manifest discipline. Stars may or may not factor into this system. Regardless, the structural, mathematical, and proportional rigor remains indisputable. The pyramid's geometry speaks even if the sky remains silent. And so the search for an astronomical purpose is informative but incomplete. While Orion and Sirius hypotheses provide a compelling narrative, they do not explain the entirety of the pyramid's design. Precision exists independently of celestial alignment. The angles, ratios, and concavities persist regardless of the stars. The Great Pyramid continues to assert a singular fact: its geometry is deliberate, its proportions are coherent, its orientation is exceptional, and even when potential astronomical correlations are entertained, They do not replace the evidence of measurable intent embedded within the stone. If stars cannot fully explain the Great Pyramid, the structure still communicates. Its message is in the angles, the slopes, the concave faces, and the internal passages. Geometry remains its language, precise and enduring, awaiting comprehension on terms set entirely by the builders themselves. The precise geometry of the Great Pyramid presented builders with a problem that would challenge even modern engineers: how to move millions of limestone blocks weighing up to several tons into a coherent structure that rises more than 140 meters, maintains sub-degree slope consistency, and aligns within a fraction of a degree to true north. Traditional explanations have long leaned on external ramps, often imagined as colossal linear inclines or spiraling embankments. Yet when subjected to structural and geometric scrutiny, these models reveal severe limitations. An external straight ramp extending from ground level to the apex would have had to rise at a slope manageable for hauling heavy blocks, typically no more than 10 to 12 degrees to avoid overexertion or accidents. Given the pyramid's height, this implies a ramp more than 1.5 kilometers long. The mass of stone required to build such a ramp would exceed that of the pyramid itself, creating a logistical paradox. To build the pyramid, you must first build an impossibly massive ramp. Spiral ramps, proposed as alternatives, encounter different obstacles. As the ramp winds around the pyramid's exterior, it interferes with alignment lines and obscures the geometry of the faces. Maintaining precise slope angles and concavity along an exterior spiral would have required extraordinary adjustments, effectively negating the pyramid's mathematical uniformity. This is where the internal ramp hypothesis, championed by Jean-Pierre Houdin, offers a compelling alternative. Instead of an external appendage, the ramp exists within the pyramid itself, concealed in a series of corbelled passages along one face. Using this method, builders could raise blocks incrementally along a protected linear path, maintaining control over slope, orientation, and placement. Structural simulations suggest that internal ramps could accommodate stone transport without disturbing the pyramid's precise geometry, a feat that external ramps struggle to achieve. Concavity plays a subtle yet essential role in this theory. Each inward bending face creates a natural corridor along the edge, slightly recessed from the pyramid's visual plane. This recess could have served multiple purposes during construction. First, it provides an anchor point. Blocks moved along an internal path are guided by predictable reference planes, reducing the likelihood of misalignment. Second, the concavity might assist in load distribution. By reducing the external width at certain vertical sections, inward-facing planes slightly alter stress patterns, channeling weight toward the pyramid's core and corners. The result is not only a stable structure, but also one that allows controlled, incremental assembly. Corner locking is another key engineering consideration. The pyramid's four corners function as natural braces, stabilizing adjacent faces and distributing compressive forces. By moving blocks along an internal ramp, workers could place stones sequentially against these corners, leveraging the geometry to ensure structural cohesion from the bottom upward. Each block becomes both a component and a stabilizer, integrating into a network of interdependent forces. Houdin's simulations indicate that this method reduces lateral stress and prevents cumulative errors that might otherwise distort face alignment or apex placement. The internal ramp also offers a plausible solution to the question of apex precision. The top of the pyramid represents the convergence of four meticulously angled faces. External ramps make it difficult to deliver the final stones without risking misalignment or damaging completed sections. An internal ramp, however, allows for last-meter adjustments using small teams, guided by precise geometric references along the ramp walls. The apex is not reached by brute force, but by controlled incremental movement, ensuring that slope, concavity, and alignment converge accurately. Evidence for internal ramp feasibility is supported by modern structural simulations. Houdin and collaborators used computer modeling to analyze stress distribution, load transfer, and block placement efficiency. Results show that an internal ramp reduces friction, lowers the risk of tipping or displacement, and preserves face geometry throughout construction. The simulations also highlight that the pyramid's concave design could serve as both a guide and a stabilizing feature, suggesting that what appears as a minor aesthetic deviation may have been an engineering tool. Material logistics are also consistent with this approach. Limestone for the core and casing stones was sourced from nearby quarries. By building an internal ramp along the pyramid's northern face, workers could transport blocks from quarries or staging areas without extensive external scaffolding. This approach reduces exposure to environmental factors, including sand erosion and temperature extremes, which could compromise external ramp construction. Internal ramps also shield workers from the risk of external collapse, a non-trivial consideration when moving heavy stone in a desert environment. Internal ramps do not preclude external assistance. Houdin's model allows for small, temporary ramps for initial stages or for leveling foundation stones. Yet the majority of vertical transport, especially beyond the halfway point of the pyramid, could plausibly rely on concealed passageways, minimizing material requirements while maintaining geometric fidelity. This aligns with archaeological evidence. The absence of massive external ramp remnants at Giza has long been a point of contention for traditional ramp theories. Another consideration is construction sequencing. Internal ramps allow multiple teams to work simultaneously on different pyramid levels without interfering with each other. As a block is transported upward, another team could be laying stones on lower tiers, guided by precise geometric markers on the ramp walls. This modular approach would have enabled the construction of the pyramid within the historically accepted timeline, which external ramps alone make difficult to reconcile. Houdin's proposal is further supported by subtle architectural features inside the pyramid. Some corbelled voids, previously thought to be purely structural, align with the potential path of an internal ramp. While no conclusive excavation has confirmed the ramp's existence, these voids match predictions made by structural modeling in terms of location, angle, and volume. In effect, the pyramid's internal architecture offers breadcrumbs consistent with a concealed transport system. Load transfer analysis also reinforces this hypothesis. As stones ascend, their weight is partially borne by the ramp walls and partially by the pyramid's core. This dual support minimizes stress on the faces, preserves concavity, and maintains angular precision. By contrast, external ramps place load directly against completed surfaces, risking deformation and incremental misalignment, problems that Houdin's internal ramp circumvents. Finally, the model provides a plausible explanation for some of the pyramid's more enigmatic features. The so-called notches along the northern face, previously dismissed as imperfections, could represent temporary access points for internal ramp construction or adjustment. They do not disrupt external geometry, but may have facilitated block placement and movement during critical stages of construction. Taken together, the evidence paints a picture of methodical, internally coherent construction. The Great Pyramid is not simply the product of brute labor, it is an application of geometry to engineering, where concavity, slope, corner placement, and potentially concealed ramps interact to achieve an extraordinary outcome. This framework explains how builders could maintain face concavity, apex alignment, and angular precision without the need for impractically massive external ramps. Yet questions remain. If an internal ramp existed, why has it left so little trace? Stone can erode, passages can collapse, but the absence of concrete evidence challenges archaeologists to reconcile plausibility with empirical observation. Modern robotic exploration and muon scanning have revealed voids above the Grand Gallery, suggesting that hidden spaces could persist, spaces that may correspond at least partially to internal transport pathways. The potential remains tantalizing, but definitive proof has yet to emerge. The method of construction, therefore, is not speculative imagination. It is an engineering problem solved within the constraints of geometry, material, and manpower. Concavity may have assisted alignment. Internal ramps could have allowed precise incremental assembly. Corner locking and load transfer were integral to ensuring stability throughout construction. And yet, much of this remains invisible, encoded not in ceremonial inscription, but in the discipline of the stones themselves. If internal ramps carried the weight of the pyramid upward, carefully guiding each block into its mathematically predetermined position, one wonders what remnants, subtle or hidden, might still exist within the limestone. Could further scanning and structural analysis finally reveal the paths taken by the builders who moved millions of stones with unprecedented precision? The answers may lie still beneath the surface, waiting for methods sophisticated enough to detect them. Even after millennia of study, the Great Pyramid continued to conceal secrets that could not be revealed by human sight alone. Modern archaeology had long relied on line-of-sight surveying, laser scanning, and ground-penetrating radar. Yet all these methods were limited by stone thickness, void density, and internal complexity. It was only when physicists brought particle detection into the field that the pyramid truly began to look back at humanity, revealing dimensions hidden even from the most meticulous Egyptologist. The key technology is Muon radiography. Muons are subatomic particles generated when cosmic rays strike the Earth's atmosphere. They rain down constantly, penetrating solid material far more effectively than X-rays. Critically, their passage can be measured. Dense materials, such as limestone, absorb muons more effectively than voids, producing detectable variations. By placing detectors inside, outside, and around the pyramid, researchers can track muon flux, effectively creating a three-dimensional map of empty spaces hidden within the massive stone structure. This technique was first applied seriously to the Great Pyramid by the Scan Pyramids project beginning in 2015. Teams of physicists, engineers, and archaeologists deployed multiple detector technologies, including nuclear emulsion plates, scintillator panels, and gas detectors, to triangulate muon trajectories. Unlike traditional surveying, muon radiography does not require physical access to internal spaces. It detects anomalies simply by measuring what passes through stone, allowing scientists to see inside without excavation. The first major revelation came in 2017, when Muon scans indicated the presence of a previously unknown void above the Grand Gallery. This cavity, roughly 30 meters in length, was invisible to previous methods, hidden beneath layers of massive limestone and granite blocks. Dubbed the Big Void, its discovery was unprecedented. It was the first substantial new internal space identified in the Great Pyramid in over a century. Nature published the findings, emphasizing the reliability of the multiple detector types and the statistical certainty of the measurement. The geometric implications are striking. The Big Void is aligned with the central axis of the pyramid and sits directly above the Grand Gallery, suggesting that it is not a random anomaly. Its position mirrors the internal symmetry of the pyramid, reinforcing the idea that every internal dimension was carefully considered. While its function remains unknown, its location implies deliberate architectural planning rather than incidental space. Several hypotheses have been proposed regarding the void's purpose. Structural interpretations suggest that it may function as a relieving chamber, similar in concept to the 5 smaller relieving spaces above the king's chamber. These chambers distribute the immense weight of the pyramid above critical points, preventing collapse. Yet the Big Void is significantly larger than these known spaces, and its exact role in load transfer remains unmodeled. Other theories propose symbolic or ritual significance, potentially reflecting the Egyptian emphasis on corridors, ascension, or metaphysical pathways. What is undeniable is that the Big Void exists independently of prior assumptions. It was neither anticipated by classical Egyptologists nor detectable through conventional excavation. Its discovery demonstrates that the pyramid's internal geometry is still partially unreadable, waiting for technologies capable of probing beyond human vision. In essence, the pyramid has outpaced centuries of observation, speaking only when approached with methods capable of penetrating stone at the particle level. Muon radiography itself is a triumph of interdisciplinary science. The project required particle physics expertise, computational modeling, and architectural understanding. Detectors must be calibrated to account for cosmic ray flux, material density, and angular trajectory. Large data sets of muon trajectories are collected over weeks or months to produce statistically significant maps. Advanced algorithms reconstruct three-dimensional spaces from minute differences in particle absorption. Without modern physics, the big void would remain invisible, a silent testament to the pyramid's complexity. The discovery also highlights the scale of unknowns within the pyramid. If one void of this magnitude exists directly above the Grand Gallery, then the internal volume of the structure may be far more complex than previously imagined. Smaller cavities, structural anomalies, or chambers with geometric significance could remain undetected. Muon radiography provides a method to uncover these features systematically, potentially rewriting our understanding of internal planning and proportional design. Equally significant is the relationship between the big void and the pyramid's exterior geometry. Its axis coincides almost perfectly with the pyramid's central vertical alignment. The proportional logic governing the faces, slopes, and corners appears to extend into this concealed interior space. This strengthens the argument that the pyramid is not merely a tomb or symbolic object, but a carefully orchestrated geometric system in which internal voids, corridors, and external faces operate according to consistent principles. Further studies in 2023 refined these measurements, confirming the void's length, cross-sectional area, and location relative to known chambers. Multiple detector types converged on the same result, ruling out statistical flukes or measurement errors. Researchers noted minor discrepancies in width along the void's length, suggesting that it may taper or contain internal subdivisions, features impossible to observe without additional muon detection or eventual physical inspection. The big void also raises engineering questions. How did the builders achieve such a large empty space without compromising the pyramid's structural stability? The surrounding masonry is aligned, the walls remain stress-bearing, and no evidence exists. This implies advanced knowledge of load distribution and weight management. In effect, the internal architecture anticipated modern engineering challenges, maintaining geometric coherence while creating significant empty volumes. Muon radiography, therefore, does more than detect voids. It validates the discipline of construction methods, confirming that the internal layout was deliberate and geometrically consistent. It demonstrates that the builders were not merely stacking stones but orchestrating spaces, forces, and dimensions to achieve structural and proportional fidelity. The pyramid continues to assert its precision, now verified at the subatomic level. Importantly, the big void underscores a methodological principle for modern study. Some aspects of monumental architecture can only be understood through tools outside traditional archaeology. Particle physics, computational modeling, and non-invasive probing allow us to engage with the pyramid's geometry in ways unavailable to previous generations. This sets a precedent. If further unknown cavities exist, we will likely discover them through advanced detection methods rather than by excavation or speculation. The discovery of the big void also illustrates a larger pattern. Just as the pyramid's concave faces remained invisible to ground observers and internal ramps left no overt trace, so too do its hidden cavities resist casual detection. Geometry, proportion, and construction logic operate on scales and in spaces inaccessible without specialized instrumentation. Muons reveal only a fraction of the pyramid's internal story, leaving open the possibility that additional voids, smaller, strategically placed or aligned along geometric axes, await discovery. So, the big void is a proof of principle. It confirms that the Great Pyramid contains previously unknown internal spaces that are geometrically significant, aligned with the core structure, and executed with the same rigor as exterior faces and slopes. Muon radiography bridges millennia, allowing the pyramid to communicate through particles, revealing dimensions that were deliberately hidden or structurally necessary, yet invisible. The Big Void, discovered above the Grand Gallery, immediately drew the imagination of scholars and enthusiasts alike. Popular accounts quickly labeled it a hidden chamber or even a secret room, implying ceremonial or ritual function. Yet a closer methodical examination rooted in structural engineering and architectural logic suggests a different interpretation. The void exists less as a room to be occupied and more as a geometrically and structurally functional space. Its dimensions, roughly 30 meters long and comparable in height to the Grand Gallery, do not conform to conventional chamber proportions. The ends do not terminate in sarcophagus-sized niches or doorways. No inscriptions, fittings, or artifacts have been found, which distinguishes it sharply from other internal spaces. The Big Void is devoid of human-centric features. It is not designed to be inhabited, accessed, or ceremonially significant in any traditional sense. This absence is meaningful. It demonstrates that space itself can serve as a structural or symbolic instrument without being a conventional room. Structural engineering provides insight. The pyramid's immense weight, millions of limestone blocks totaling over 6 million tons, must be distributed in a manner that prevents collapse. Known relieving chambers above the king's chamber illustrate how voids are integrated intentionally to redirect stress. By creating a hollow area directly above critical load points, the pyramid channels compressive forces around key structural elements. The Big Void, sitting above the Grand Gallery, is in a similar position. Finite element modeling shows that a cavity of this size can serve to reduce vertical pressure on lower passageways while maintaining the integrity of the surrounding masonry. In essence, emptiness becomes a tool for precision load management. Beyond structural relief, voids can also reflect construction sequencing strategies. Moving multi-ton blocks vertically requires temporary adjustments in the interior geometry. Creating a void could allow incremental movement and temporary staging of blocks without disrupting already placed courses. In this view, the void is a negative space deliberately incorporated to facilitate construction rather than a destination or functional chamber. Such a design emphasizes planning, foresight, and integration of the internal architecture with the logistical needs of large-scale assembly. The concept of absence as design resonates in broader architectural history, though rarely at this scale. Architects have long used empty volumes to guide perception, control load paths, or define circulation. In the case of the Great Pyramid, absence is formalized. It is precisely measured, aligned along the central axis, and positioned within a broader proportional system. The void mirrors the pyramid's external symmetry and slope ratios, suggesting that even empty spaces obey the same mathematical discipline as solid faces. This perspective challenges traditional notions of what constitutes purposeful construction. In modern engineering, negative space, voids, recesses, or cantilevered areas serves both structural and aesthetic functions. The Big Void may be an ancient analog of these principles, but on a monumental, almost unprecedented scale. Its precision implies intention. This is not a mistake, not a collapsed chamber, and not a convenience of material shortage. The void was designed, measured, and integrated within the pyramid's overarching geometry. Scan pyramids interpretations support this careful approach. Researchers emphasize that voids should be understood first as geometric phenomena rather than ceremonial spaces. The statistical alignment of the void with the Grand Gallery, the constancy of its height along its length, and its direct relation to the pyramid's central axis all suggest a design-driven rationale. Its presence allows for a more coherent reading of internal geometry. The pyramid's internal volumes, solid and empty alike, form a proportional network, echoing the logic imposed on exterior faces, slope angles, and corner alignment. Moreover, thinking of the void as functional absence reframes its relationship to other interior features. The King's Chamber, Queen's Chamber, Ascending Corridor, and Grand Gallery all exhibit careful geometric planning. The void above the Grand Gallery becomes an extension of this discipline. It preserves vertical alignment, reinforces structural ratios, and may have accommodated construction techniques such as temporary scaffolding or internal ramps. Its size and orientation are too precise to be incidental. The void also challenges the human-centric view of space. Most pyramidal research assumes that every empty area is intended for people, objects, or ritual. But in the context of the Great Pyramid, emptiness itself carries mathematical and architectural meaning. By leaving a deliberate cavity, the builders could manipulate internal forces, maintain proportional integrity, and encode geometry without the need for occupancy. In this sense, the pyramid's internal logic transcends human scale. It is a system designed to function structurally, proportionally, and mathematically, independent of immediate use. Negative space also interacts with the pyramid's external features. The concave faces, precise slope angles, and cardinal alignment all impose constraints on the interior. By integrating voids such as the Big Void, the builders could maintain these constraints while creating a safer, more manageable construction process. The void is therefore not merely empty, it is active. It participates in the architectural dialogue between load, form, and proportion. Finally, the precision of the void suggests that geometry alone can be the purpose of space. Its alignment along the central axis, consistent height, and correspondence with structural elements indicate that the pyramid's architects treated space itself as a variable in design. This is a radical approach for a structure over 4,500 years old. It indicates foresight and comprehension of spatial dynamics that remain relevant in modern structural engineering. The Big Void exemplifies the principle of geometry without chambers. It is too precise to be accidental, too aligned to be decorative, and too positionally consistent to be coincidental. Its function is not ritual, ceremonial, or human-centric. It is mathematical, structural, and integral to construction sequencing. The void demonstrates that absence can be as deliberate as presence, that negative space can carry the same proportional discipline as solid stone, and that the pyramid's internal architecture extends far beyond what is visible or accessible. And so the question arises naturally. If space itself can be designed with such precision, what does it mean to leave emptiness in stone? What hidden logic or construction imperative dictated the careful creation of a void that obeys the pyramid's geometry as faithfully as its walls? The Great Pyramid cannot be understood by isolating its parts. Its faces, slopes, shafts, and internal voids were designed not as discrete features, but as components of an interconnected whole. Each element interacts with the others, forming a system whose complexity and coherence extend across both visible and hidden dimensions. Viewed from this perspective, the pyramid is less a monument in the conventional sense, and more an engineered spatial and geometric network in which every measurement, angle, and void participates in a larger structural logic. The exterior concavity, previously dismissed as erosion or aesthetic whim, gains new significance when considered as part of a systemic design. The inward bending faces subtly alter load distribution along each edge and across the pyramid's base. They affect the interaction of sunlight, casting specific shadow patterns that correspond to precise angles and axes. The concavity also guides perception. From the ground, the pyramid appears flat-sided, preserving the illusion of simplicity, while from above, under specific illumination, it reveals 8 distinct planar faces. The interplay of light, structure, and measurement demonstrates a careful calibration of optical and geometric systems where the pyramid communicates differently depending on the observer's vantage point. Orientation is another layer of integration. The alignment of the pyramid to true north within 0.05 degrees is extraordinary for its era. This precision is not merely a ceremonial nod to cardinal directions, it interacts with the structure's internal geometry. The face's concavity, slope ratios, and central axis are aligned so that vertical voids, ramps, and internal chambers fit seamlessly within the external plan. Deviations as small as a fraction of a degree could disrupt this coordination, yet the pyramid maintains remarkable consistency across multiple scales, from millimeter-level masonry tolerances to global orientation. The system is holistic. The exterior and interior cannot be considered independently without losing the coherence that defines the pyramid's geometry. Internal angles, including the enigmatic king's and queen's chamber shafts, continue this principle. Their inclinations, while functionally ambiguous, reinforce the pyramid's axial symmetry. Shafts may have been designed as conduits for airflow, symbolic references, or construction tools, but whatever their purpose, they obey the same mathematical rules as external faces and slopes. Their position, angle, and termination align with proportional ratios embedded in the pyramid's base, face concavity, and apex convergence. In a systems context, these angles are not anomalies. They are nodes within an internal network that mirrors the pyramid's exterior. Each shaft interacts with load distribution, slope geometry, and void placement, contributing to an invisible yet measurable internal logic. The big void, revealed by Muon radiography, reinforces the systemic interpretation. Its location above the Grand Gallery is not random. It corresponds to the pyramid's central axis, maintains proportional height relative to surrounding chambers, and preserves stress management across multiple layers of masonry. Its precision suggests that voids were not afterthoughts or incidental cavities, but integrated components designed to balance internal forces, facilitate construction sequencing, or define negative space as part of the geometric system. Its presence demonstrates that the pyramid is not simply solid stone with chambers carved into it. It is a dynamic structure, with both mass and emptiness carefully orchestrated to create structural and proportional equilibrium. Viewed through the lens of systems engineering, the pyramid resembles a network of interdependent modules. Each face, slope, shaft, and void functions as part of a broader feedback loop. Changes in one element affect the others. Concave faces influence load distribution, which interacts with chamber placement. Chamber angles affect stress pathways, which in turn inform void location. Voids affect both construction sequencing and long-term structural stability. The design operates across scales, from millimeters in stone dressing to tens of meters in internal voids, yet it preserves proportional fidelity throughout. This multi-scale integration is remarkable, particularly given the technological tools available in the Old Kingdom. This systems perspective also explains why no single feature provides a complete explanation. The concavity alone does not account for alignment. Shafts alone do not explain construction precision. Voids alone do not justify slope ratios. Each feature must be understood in relation to the others, as part of a coordinated network. Randomness is impossible. The repeated application of geometry across scales, combined with the alignment of physical and proportional axes, indicates intentional design and rigorous planning. The pyramid is a composite entity, with emergent properties that only appear when the system is viewed in totality. Modern structural modeling reinforces this interpretation. Finite element simulations demonstrate that the pyramid's internal geometry, when considered together, optimizes stress distribution, minimizes potential deformation, and preserves slope accuracy. Internal voids, concave faces, and corner alignment act synergistically. Even subtle adjustments in slope or concavity produce measurable changes in load pathways, demonstrating that these features are interdependent rather than decorative or coincidental. In effect, the pyramid functions as a mechanical geometric system, where internal structure, external form, and proportional logic all coalesce to maintain equilibrium. This integrated perspective also sheds light on construction methods. An internal ramp, guided by the system's geometry, could transport stones along axes predetermined by slope ratios, corner positions, and concavity. Each block would be placed in a manner consistent with both local structural requirements and the broader proportional system. Temporary voids or passages could facilitate movement without compromising stability. In other words, construction and design were co-evolutionary processes, each informed by the system's constraints and feedback loops. Importantly, this interpretation reframes our understanding of the pyramid's purpose. It is not merely a tomb or symbolic object, it is an optimized geometric and structural system. Its design anticipates both material properties and environmental forces, distributing weight, preserving alignment, and maintaining proportional coherence across millennia. Geometry is not incidental, it is the operating principle of the system. The pyramid demonstrates an advanced understanding of both architecture and what we would today call systems engineering, long before these concepts existed formally. Even the pyramid's apparent simplicity, a four-sided structure with a pointed apex, conceals the depth of its systemic complexity. The concave faces, subtle slope ratios, internal shafts and voids interact across scales, from the microscopic precision of masonry to the macroscopic alignment with cardinal points. Each feature is both independent and dependent, forming a network that is resilient, coherent, and deliberate. Random construction, improvisation, or coincidence cannot account for this level of integrated precision. Thus, the Great Pyramid must be understood as an integrated whole, a structure in which geometry, engineering, and internal logic converge. Exterior and interior, solid and void, visible and hidden, all operate as components of a unified system. Only by considering these elements collectively can the full scope of the pyramid's design be appreciated. And if the pyramid is a system, deliberately structured, precisely measured, and interdependent across scales, the natural question emerges: what was it optimized for? Was it intended to preserve structural stability, facilitate construction, encode proportional ratios, or something entirely beyond our current understanding? The answer remains elusive, but the systemic perspective offers a framework for asking questions that honor both the precision and the ambition of its builders. Despite centuries of fascination, much of what has been written about the Great Pyramid falls into speculation rather than evidence. Popular culture often presents extraordinary claims, power plant theories, energy generation, or alien intervention, as if they were plausible explanations for the pyramid's precision and scale. A careful, skeptical approach is essential, particularly when addressing an audience capable of critical reasoning and an appreciation for scientific method. The so-called power plant theory gained traction in the late 20th century. Proponents suggest that the pyramid was designed to generate or transmit energy, often citing the precise angles of the faces, the internal voids, and the alignment to cardinal directions as functional components of an ancient technology. While such ideas are visually striking and narratively compelling, they lack measurable evidence. No residual energy, machinery, or functional components have ever been detected. Engineering analysis indicates that the pyramid's materials, primarily limestone and granite, do not possess the properties required to generate electricity or transmit energy in the manner proposed. From a physics standpoint, the internal voids, ramps, and concave faces are entirely consistent with structural and geometric purposes, leaving no empirical gap to be filled by exotic energy explanations. Similarly, alien intervention theories have proliferated in popular media. These arguments claim that the pyramid's precision, alignment, and scale are too advanced for ancient Egyptians, implying external assistance. Skeptical examination, however, highlights both historical context and technical feasibility. Ancient Egypt had access to simple machines, ramps, levers, rollers, and possessed sophisticated knowledge of geometry, astronomy, and materials. Experimental archaeology and engineering simulations have repeatedly demonstrated that the pyramid could have been constructed with these tools and methods. The existence of an internal ramp, corner-locking techniques and precision surveying is entirely human in origin. Claiming alien intervention ignores centuries of empirical evidence and dismisses human ingenuity. Precision and foresight in construction are remarkable, but they are human achievements, not extraterrestrial anomalies. Skepticism also requires recognition of the limits of evidence. Modern technologies, including Muon radiography, have revealed voids like the Big Void and subtle internal corridors. Yet these discoveries tell us what exists, not why it exists. They reveal geometry, mass distribution, and load pathways, but they do not confirm symbolic intent, ritual function, or hidden energy systems. To extrapolate from geometric precision to metaphysical or technological conclusions is to step beyond what the data can support. Maintaining this boundary is critical. The pyramid communicates through measurable geometry and construction logic, but it does not leave a manual for interpretation. The danger of over-explanation lies in the human tendency to force narrative onto ambiguity. Because the pyramid contains anomalies, concave faces, shafts without apparent function, hidden voids, there is a temptation to attribute these features to extraordinary causes. Skepticism encourages restraint. Every hypothesis must be weighed against evidence, not narrative appeal. The concave faces, for example, are mathematically measurable and structurally defensible. The shafts are precisely angled but terminate within solid stone. The Big Void exists, but its function is inferred from position and proportion, not historical record. Each feature invites interpretation, but the interpretations must remain grounded in observation and logic. Scientific skepticism also applies to chronology and historical context. Many speculative claims ignore the engineering knowledge of the Old Kingdom. Surveying techniques based on circumpolar stars, knowledge of material properties, and logistical strategies for moving limestone blocks are well documented. The pyramid's builders were capable of remarkable precision using these techniques alone. No additional technology is required to explain construction or alignment. The evidence consistently supports a human, methodical process rather than extraordinary mechanisms. Importantly, skepticism does not equate to dismissal of mystery. A skeptical approach recognizes the limits of current understanding while remaining open to future discovery. We do not yet know why the concave faces were designed, why the Big Void exists precisely where it does, or how the internal network of geometry, ramps, and voids fully functioned. Rejecting myths and unfounded claims is not the same as claiming a final answer. It simply clears the ground for questions that can be addressed with evidence and method. Skepticism also protects credibility. For an audience of thoughtful viewers, presenting extraordinary claims without substantiation risks undermining trust. By calmly rejecting unsupported theories, acknowledging what we do not know, and highlighting the rigor of verified observations, we reinforce the authority of scientific investigation. The Great Pyramid is remarkable not because of invented explanations, but because its precision, geometry, and internal planning continue to challenge understanding, even under disciplined analysis. Finally, this skeptical framework emphasizes observation over speculation. The pyramid's alignment, concavity, voids, and internal architecture can all be measured, modeled, and tested. Explanations grounded in physics, structural engineering, and historical methods provide an actionable understanding. Speculative ideas about hidden energy systems or alien construction, while sensational, do not yield testable predictions and therefore fall outside responsible inquiry. By rejecting these unsupported explanations, we are left with a more difficult but intellectually honest challenge: understanding the Great Pyramid on its own terms. The structure is neither a machine nor an alien artifact. It is a human creation of extraordinary geometric and engineering sophistication. It presents questions that cannot be answered by invention or conjecture, only by careful observation, measurement, and reasoned interpretation. Even in the modern era, with laser-guided machinery, computerized modeling, and highly standardized materials, replicating the precision of the Great Pyramid remains a profound challenge. Contemporary construction tolerances typically allow deviations of several millimeters per meter in high-precision projects. By contrast, the pyramid's base, spanning over 230 meters per side, aligns to true north within 0.05 degrees, and its faces exhibit concavity so consistent that all 8 planar surfaces converge symmetrically, visible only under the right light. Achieving such precision without modern tools illustrates a measurement culture that was both sophisticated and disciplined, embedded deeply into the planning and execution of construction. The pyramid demonstrates that geometry was not incidental or decorative. Each angle, slope, and internal void appears deliberately calculated. Concavity is aligned with the apex, slope ratios maintain proportional consistency, and internal features such as the grand gallery and hidden voids adhere to a coherent geometric framework. Modern structural simulations show that these measurements are not only mathematically impressive, but also serve practical functions: stress distribution, load transfer, and facilitation of construction sequencing. Ancient builders integrated both aesthetic and functional imperatives, yet always underpinned by precise calculation rather than improvisation. This level of precision reveals a broader worldview. The pyramid's geometry reflects a belief in the order of space itself, an understanding that alignment, proportion, and structural coherence are not merely technical concerns but manifestations of a larger cosmic or architectural logic. For the builders, measurement was a guiding principle, a way of organizing matter, labor, and thought. Every stone became a component in a system where error was minimized and proportional relationships were preserved across multiple scales. Modern engineers attempting to replicate similar feats face challenges that extend beyond technology. Tools alone cannot replicate the discipline, planning, and iterative verification inherent in the original construction. The pyramid exemplifies a cultural approach to precision. It is a mindset in which geometry governs action, where adherence to measurement is both a practical requirement and a philosophical commitment. In this sense, the pyramid is not merely a monument. It is a physical embodiment of a worldview that revered proportionality, symmetry, and alignment as essential principles. The implications extend beyond engineering. The pyramid teaches that extreme precision is not only achievable, but sustainable when embedded in a system of knowledge, culture, and practice. Its geometry transcends utility or ornamentation. It communicates intention, method, and disciplined foresight. Even today, the pyramid serves as a benchmark against which modern construction, measurement, and systems thinking are measured. Ultimately, the pyramid challenges us to reconsider what precision can mean. It is not just a matter of technical ability, it is a manifestation of thought, planning, and cultural commitment. The geometry is a message of capability, discipline, and vision encoded in stone, surviving millennia with remarkable fidelity. And so the question remains: if such geometry reflects both skill and worldview, what does it reveal about the minds and methods of those who built the Great Pyramid? Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.